Okay, from this lecture, we will start discussing about geometric representation of algebraic numbers. So, geometric representation of algebraic numbers. Okay, and to do that, the first thing we require is some prerequisites, which we will be doing in this lecture, and in the next lecture we will be going into the core discussion of whatever we are intended to do in this very specific topic. Okay, so now what is an algebraic number typically? So on a general note, we have what we call algebraic elements. So suppose k over f is a field extension. Suppose k over f is a field extension. Simply speaking, that f is a subfield of k. Okay. K is a field and f is a subfield of k. This we call as that k is a field extension of it. So suppose k over f is a field extension, then an element alpha in k is said to be algebraic if alpha is a root of some polynomial. If alpha is a root of some polynomial over f. Okay. If k is the complex field and f is the rational field, then alpha is said to be an algebraic number. Clear? For example, simple example, root 2, if I take the element root 2 from C, then I'll see that root 2 is, let me write it in this way. Okay, one sec. Yeah. So let root 2 be coming from C. Consider the rational polynomial fx, which I can write as x squared minus 2. This surely comes from the field of polynomials, the ring of polynomials over Q. And clearly, f of root 2 is 0. Okay, therefore root 2 is an algebraic number. Clear? Okay. For example, pi, which is an element from C, is not algebraic over Q. Okay. For example, E is also not algebraic over Q. Okay. So whenever we talk about the field extensions where the superfield is the complex field and the subfield is Q, then these algebraic elements are simply called algebraic numbers. And I hope you have already understood what we mean by an algebraic number. So these are all those complex numbers which are roots or which can be expressed as roots of some polynomial over the rational field. Okay. Now let let alpha in C be algebraic. Whenever I say algebraic, I mean algebraic over Q, or let precisely be writing it as be algebraic over Q. Okay, or it's an algebraic number, whatever term you want to use. Okay, then we can consider a map which we often call the evaluation map. Consider the map phi alpha, which takes elements from Qt to C, and what it does is that it takes an element which should be a polynomial over Q, so ft, and it evaluates this polynomial at alpha. Clear? Now since alpha is algebraic over Q, I know that there exists a polynomial over Q such that that polynomial evaluated at alpha is 0. Or in other words, since since alpha is algebraic, therefore there exists some polynomial pt, or let me for now use it as qt, in capital QT, such that q of alpha is 0, right? This immediately means that the kernel of this map is non-zero, right? There exists a non-zero polynomial such that so I should also mention that there exists some non-zero polynomial, okay, such that that polynomial evaluated at alpha is 0. So I should also add this up here where I defined algebra. So it of some non-zero polynomial, to be precise, because a zero polynomial is not to be considered, obviously, for obvious reasons, right? So kernel of phi of alpha is not a zero ideal, and you can easily check that this is indeed a well-defined ring homomorphism. Thing to observe is that, but we know that the ring of polynomials over Q is a PID, is a principal ideal domain, which implies that the kernel of phi alpha, this is an ideal of this principal ideal domain Qt, so it must be generated by some monic irreducible polynomial, where Pt is some monic irreducible polynomial over Q. Okay, clearly enough, by definition of the ideal generated by some element, if so clearly enough, firstly, that P of alpha is 0, because it should itself be inside the ideal generated by it, and if f of alpha is 0 for any f over Q, then this P must surely divide f. Division will happen obviously inside the ring of the ring of polynomials over P. Clear? This P is what we call the minimal polynomial of alpha over Q. Okay, so let me just add it on a general note. In general, if K over F is a field extension, then and suppose alpha in K is algebraic, then there exists a map phi alpha from so it will take elements from Ft, map it to K, such that phi of alpha evaluated of any polynomial is just that polynomial evaluated at alpha. Kernel of this map will be non-zero, and the reason of this we have already seen, because there exists some polynomial such that that polynomial evaluated at alpha must be 0, and the polynomial itself is a non-zero polynomial. So the kernel of is 0, which implies that this kernel must be generated by some element Pt, right? Because we are talking about the ring of polynomials of a field, right? And so it comes out to be a principal ideal domain. So, and this P is called the minimal polynomial of alpha over F, right? So whatever we are discussing about these algebraic numbers, or specifically the field extension C over Q, these are in fact general notions, and we have just restricted us to these two fields. Okay. So I won't be discussing the general notions anymore. I will be specifically simply talking about these field extensions C and Q and elements within these field extensions. And you can obviously, while just reading the definitions, you can in fact have an intuition that these are actually general notions. Okay. If alpha in C as a field extension over Q is algebraic, then now C over Q forms a well-defined vector space, right? Because C is itself an additive abelian group, and whenever I choose any element out from Q and multiply that element to a complex number, the resulting element is still a complex number. And the rest of the properties of the scalar multiplication of vector spaces, these holds trivially due to commutativity and also and associativity and distributivity. Those are very trivial notions of these elements. So then the dimension of C considered as a vector space over Q, then the dimension of C considered as a vector space over Q, this is also written as sorry, I'm not talking about this. I need something more to talk about first. Sorry. So then the field Q alpha is the smallest field extension of Q containing alpha. Okay. And the elements, or rather I can simply see containing alpha. Now Q of alpha Q, so and I write it as Q, so this forms a well defined vector space over Q, just due to the reason of how C forms. So the basis of Q alpha as a vector space over Q is the elements 1 alpha alpha squared till alpha n minus 1. Clear? Where the degree of the minimal polynomial which surely exists for alpha is an algebraic element, algebraic number, so degree of the minimal polynomial of alpha is n. Okay. So what we typically get is that therefore dimension of Q alpha, so this is often called the field generated by alpha, the field extension generated by alpha. Okay. Or this is often called a simple extension over Q due to alpha. So dimension of Q alpha as a vector space over Q, which is also written as Q alpha colon Q. Okay. And this is exactly equals to the degree of the minimal polynomial of alpha over Q. Okay. And this is called the degree of extension. The degree of extension of Q alpha over Q, or it's often directly said to be just the degree of alpha over Q. Clear? And all these notions are also general notions. I can talk about any arbitrary field extension K over F, and I can choose out an algebraic element over K, and I can extend F using that element to form the field F alpha. Every other properties will hold trivially, and the notions will also come out exactly same as they are doing now. Clear? Okay. Now if this degree of extension is finite, if the degree of extension, so the degree of extension basically, so in general for a field extension K over F, the degree of extension, which is basically nothing but the dimension of K as a F vector space, so in general for a field extension K over F is the degree of extension of K over F. Okay. If this degree of extension is finite, we say the extension to be a finite extension. We say the extension to be a finite extension. So now we can see this, which implies that so I can simply say that therefore this extension Q alpha over Q is a finite extension, because the degree of extension of Q of alpha over Q this is equal to the degree of the minimal polynomial of alpha over q, which surely has a finite degree, right? Therefore, it's a finite extension. Okay. And the point to observe here is that also every finite extension is an algebraic extension. And what do I mean by an algebraic extension? So let me just speak about it very briefly. So a field extension K over F is called an algebraic extension if every element of K is algebraic over F. Okay. For example, if you choose any complex number a plus ib, you will see that you will get a polynomial which is a polynomial over R of which a plus ib is a root. Okay. You can consider this as an exercise that for all a plus ib coming from C, there exists a polynomial ft coming from Rt such that f of a plus ib is equals to 0. In other words, the field extension C over R is a algebraic extension. Clear? Okay. Okay, I guess we are now good to go. So now we come to the main definition of today. Consider a field extension. Basically, these are called a tower of field extension. That is, we have intermediate fields. Okay. So we have a field extension of the form say K over F over E and so on. So I have a tower of field extensions. So definition is that C over K over Q. So that means that K is a subfield of C and Q is a subfield of K. So is said to be, I am defining this for K itself. So that's why I wrote it like this. So is said to be an algebraic number field or simply a number field. So I should emphasize on these two terms, an algebraic number field or a number field if the degree of extension of K over Q is finite, or which immediately implies that K over Q is an algebraic extension, or that every element in K is algebraic over Q. And I should also make this very clear that the statement I wrote here that every finite extension is an algebraic extension, the converse is not true. That every algebraic extension need not be a finite extension. There are certain restrictions to that. In general, that's not true. So I cannot define it immediately in terms of K over Q being an algebraic extension. The definition lies in the fact that the degree of extension of K over Q is finite. Clear? Now we come to the main goal, the primary goal of this lecture. I'll just quote it and then we will be continuing with our discussion. So, idea. So what are we trying to specifically do? So we are trying to develop a method of embedding a number field K in a real vector space of dimension equal to the degree of K, that is the degree of extension of K. And there is something more, in such a way that the ideals of K, the ideals in K mapped two lattices in this vector space. Okay, so this is the thing which we would be trying to do. And in fact, this immediately gives us a geometric representation of algebraic numbers, because whenever I try to embed this number field k inside a vector space, inside a real vector space, this number field immediately acts as if it's itself inside. I mean, see, embedding does not happen naturally. Okay, what does embedding typically mean? So it typically means that there exists some map such that the image of this there. So what I mean to say is that I want to embed this number field as a real vector space. Typically what I try to say is that there exists a map such that the image of k under that map is completely inside the real vector space. And once we can do that, and the map needs to be injective as well. This map needs to be injective, and this map needs to be some sort of a homomorphism or a linear transformation, whatever you want to see. These two terms are relative to the spaces we talk about. Whenever we talk about algebraic structures, we will use the term homomorphism. Whenever we talk about vector spaces, we will use the term linear transformations. In simple sense, is that what I mean to say is that if I have this to be k, and if I have this to be my real vector space, then I will get an injective map from k to this real vector space. Say f is injective, which would make k isomorphic to its image under f. So these two will be isomorphic, and the image of k is a subspace of R, and so it will behave as R does. Or sorry, I mean it will behave as it won't be a subspace of R. It will be a subspace of the real vector space, and it will behave as the real vector space does. It might be topologically, it might be metrically, it might be geometrically. Okay, all the properties will be then dragged to this subspace Fk, which is an isomorphic copy of k, and that is what we mean by embedding k inside a real vector space. Okay. Clear? Okay. And to do that, we need some theorems. So we'll do that first. Okay. So there's a theorem, a very small theorem, which says that let k be is equals to q theta, and let this be a number field. So if this is a number field, so this is an algebraic extension over q, which immediately speaks of the fact that theta is algebraic over q. Be a number field, so we can talk about a finite degree, so of degree n over q. Then there exists exactly n distinct monomorphisms sigma I from k to c, I ranging from 1 to n. The elements sigma I of theta, which is equals to theta I, are the distinct zeros, in C of the minimal polynomial of theta over q. Okay, so let's quickly prove this. So let theta 1, theta 2 till theta n be the zeros of the minimal polynomial. So let me just name the minimal polynomial. So of the minimal polynomial p of theta. In fact, So I can also say that these zeros are distinct. So be the distinct zeros. I can say this to be distinct for the following reason. See, if f is, so this is a general notion. If f is irreducible over k, then f and df, that is the derivative of f, then derivative of f is defined as exactly as we define the derivative for any arbitrary polynomial. So then f and df must be co-prime must be co-prime, right? So if it's co-prime, if the derivative of f and f are co-prime, therefore f cannot have repeated roots, right? And why does this happen? So I'm simply speaking of the fact because over a field of characteristic 0, since we're working over a field of characteristic 0, so over a field of characteristic 0, a non-zero polynomial, it's divisible by the square of a polynomial, which will ensure that it has repeated roots if and only if the GCD of that polynomial with its derivative is not equals to 1. Okay. Therefore, by the Bézout lemma, I can have a linear combination of these polynomials with the coefficients coming from k, and if I take this equation to the complex field, if I extend this to the complex field, I'll immediately, because the complex field, so if I extend this to the complex field, I'll immediately get that the GCD of f and df is equal to 1. Clear? Okay. Right. So each of these theta i's are the distinct zeros, and in fact each of these theta i's are also having the minimal polynomials as p. Also, okay, let me change the color. Also, each of these theta i's have a p as their minimal polynomial. Okay, because it's quite obvious that because their respective minimal polynomials will divide p, but p is irreducible, right? So they must be exactly equal to p. Due to this reason, therefore, there exists a field isomorphism. There exists a field isomorphism sigma I from q of theta, from q theta to q theta I, okay, such that sigma I of theta is simply mapped to theta I. And why does this happen typically? So I'll just give a brief of this. Because since they are having the same minimal polynomials, now how do we typically define q of theta? Okay. So if you recall the way we constructed the evaluation map, so q of theta will actually be defined as qt over quotiented over pt, where pt is the minimal polynomial of q. This isomorphism comes from the evaluation map phi evaluated at theta. Okay. And q of theta I will also be the same isomorphism, but in this case we will have the map to be phi of theta I, but we are having isomorphism. So this is isomorphic to the same map, and isomorphism is transitive in nature, so q of theta will be isomorphic to q of theta I, and the map will be immediately seen to be just mapping the element theta to theta I, because rest of the elements are easily taken care of. Okay, I hope this part is clear. In fact, if alpha is a if alpha is any polynomial, or if alpha is an element of q theta, then we know that by the basis by the basis we have of q theta, if I take any linear combination of those elements, then alpha is typically some polynomial over theta. So alpha is basically a polynomial r evaluated at theta for r coming from qt, and the degree of r is less than n. Okay, so this is the degree of the polynomial r. Okay, because what was the basis? The basis was the elements 1, theta, theta square till theta to the power n minus 1. So any arbitrary linear combination will be of the form a0 plus a1 theta plus a2 theta square, so on till an minus 1 theta to the power n minus 1. So if I take r to be the polynomial a0 plus a1x plus a2x square till an minus 1 x to the power n minus 1, then r evaluated at theta is exactly equals to alpha, and the degree of r is clearly less than n, right? And then we must have that sigma I of alpha. So it will just what will it do? So I know that sigma I maps theta to theta I. So in case of alpha, it will also map theta to theta I. So we will get the polynomial R evaluated at theta I. Clear? Okay. And what can I say about the converse? Conversely, if sigma from K to C is a monomorphism. Okay. Now, why is it a monomorphism? If you haven't seen it yet, I'll just explain it up. It is a monomorphism because this is a field. We have got a field isomorphism, and this field isomorphism is always injective, even if we extend out the codomain, right? That's the case. And that so I already need injectivity for embedding, or for monomorphism simply means injective homomorphisms. So conversely, if sigma from K to C is a monomorphism, then clearly, then sigma is identity map on Q, right? Because if under sigma two rationals are same, then the rationals themselves needs to be same, and in fact the map will be exactly equal to the rational number. Okay. And this immediately follows. You can just work it out on your own. There's nothing difficult to talk about in this case. It will, because you can just check this. So I'll just give it as a checking. Just check this using the fact that the kernel of sigma is 0 subspace. Okay. Yeah. Now if sigma is identity map on Q, then 0, which you can write as sigma of p theta, because p of theta is 0, p is the minimal polynomial of theta. But since this is this is identity map on Q, I can extend this to write it as, suppose p as a representation of the form a0 plus a1 theta, and so on till say an theta to the power n. But this is nothing but sigma of a0 plus sigma a1 times sigma theta, continue till sigma an sigma theta to the power n. But I know that sigma is identity on Q, and each of these a0, a1 till an comes from Q. So this is nothing but a0 plus a1 sigma theta, and it continues till an sigma theta to the power n. And sigma theta to the power n is nothing but sigma theta whole to the power n under properties of homomorphism, properties of ring homomorphisms. So this is nothing but p of sigma theta, okay, which implies that sigma theta equals to theta I for sum I is equals to 1 to n, because sigma theta also comes out to be a root of p, and therefore it must equal to sum of these one of these theta i's. Clear? And so that implies sigma equals to sigma I for sum, right? Okay. So let this lecture be until this much. In the next lecture, we will be introducing the vector space which we require to do in this very topic, and we will go for further discussions. So meet you guys in the next lecture.